All right, this is the Unit 1 Review Packet answer key live recording, joined by guest students. Okay, number one, we're on find the domain. So when you're finding the domain, you want to find like what the possible inputs are, like what x could be equal to. And in general, we assume that all the x values are going to work, but what we cannot do is we cannot divide by 0. So here you want to actually figure out where this is going to equal 0. So you're going to set that equal to 0 as your first step. So you're going to do x squared plus x minus 42 equals 0. We're going to solve this like normal. It's going to be x plus 7 and x minus 6. So the two places where the denominator is going to equal 0 is x equals negative 6 and x equals negative 7 and x equals 6. So our answer could be x is going to be all real numbers, but x cannot equal negative 7 and x cannot equal 6. So if you're given a fraction like this, set the denominator equal to 0, and whatever that number is not in the domain. So x is all numbers, but it's not negative 7 and it's not 6. To find the domain over here, you want to, when it's a square root, the numbers that don't work are negative numbers. So wherever it's a negative here is not going to work. So we're going to figure out where that's true. We're going to make sure that 7x minus 49 is always greater than or equal to 0. And we're going to solve that for x. So we're just going to add 49, 7x equals 49, divide by 7. So x has to be greater than or equal to 7. Okay, so that would be the domain for B. Okay. Anything below 7, this is going to be negative, which will result in like an undefined answer, so that's not going to work. So if it's a square root, all the answers need to be positive. If it's a denominator, it cannot be 0. Okay, next. Determine if the functions are even or odd. So even functions are symmetric around the y-axis, and we can see here that yes, this is even. Proof could be it's symmetric across y-axis, and it's also true that f of x is equal to f of negative x. Okay. Over here, this function is not even. It's not reflected across the y-axis. It's also not odd because it's not reflected around the origin. So this is neither here because no origin or y-axis symmetry. And then you can also say f of x does not equal f of negative x, and f of x does not equal negative f of negative x. Yes. Yeah, pause. No. All right. Number 2, identify the x values of the following types of discontinuity. Yeah, sorry about the printing here. This is not great printing. We have 3 types of discontinuity. It's jump, and then on the back side you see removable and asymptotic. So I'll do them all here. So the jump, removable, and asymptotic. Jump happens like literally when the function jumps from one y value to it and picks up at another y value. You can sort of view it as a literal jump. That's a jump right there. This one, see how the function continues, but it's like a hole has been taken out. That's removable right here. Removable. We see another removable over here. And then this right here is a vertical asymptote, and that would be the asymptotic discontinuity. Asymptotic. Okay. Is that clear? Okay, moving on. Yep, this is a blank page. Here we go. 3. So here you're asked to find where it's increasing, decreasing, where it has a relative max, where it has a relative min, where it has an absolute max. So I'll go ahead and just label it on the graph. So it is increasing from -3 right here up to -1. This is increasing. And it's also increasing from 4 to 9. So here I'm going to say increasing from -3 to -1 and 4 to 9. It's decreasing from -9 to -3. And it's decreasing from -1 to 4. Okay. Where are the relative max? So relative max happens when it goes from increasing to decreasing. It needs to have like a hump kind of shape, like a peak of a valley, a peak of a mountain, right? So this is not a relative max. This is a relative max right here at x equals -1. That's it. Only one relative max here. Relative min is the opposite. It's the bottom of the valley. So bottom of the valley is right here at -3, and again here at 4. X equals -3, x equals 4. Absolute max is the most that it ever is. So the absolute max is the highest we go. Notice that like the highest we go is this 4 right here, but see how it's open? So that means like the technical like absolute max is like 3.999999 repeating, right, forever. So we say that there is none, right? There is no absolute max because we can't determine what that number is. Whereas the absolute min, notice if we look at where it bottoms out, the lowest value, it is a filled function here. The lowest value is -7. So the absolute min would be at the coordinates -3, -7. Okay? All right, moving on. We are evaluating this function. So when you're evaluating functions with a graph, all you're doing is going to this x value and seeing what the y value is at that point. So for f of 0, we're going to go to x equals 0. We're going to go down to the y. What's the y value at 0? The y value is -3. Easy, right? For f of -6, we're going to go over to -6. We're going to go down. What's the y value at -6? It's -9. Nice. F of -1, we're going to go over to -1. What's the y value at -1? So this is where it gets a little tricky. You have two open holes down below. The function is not defined here. So you ignore the -4 and the -5. But the the 2, where it's filled, that's your y value. F of -1 is 2 because that's where it's filled. Okay? F of 3, here, it's completely open. There is no filled at all. So that's undefined. F of 2 is just 1, and f of 5 not on the graph at all, so that is also undefined. So only if it's solid, only if it's filled does it have an output. If it is not, if it's open or there's nothing there, it's undefined. Okay? All right, this is a piecewise function algebraically. So for piecewise functions algebraically, very, very similar idea. You take that x value, you're plugging it into the function, but instead of like visually looking for the y value, you're actually plugging it into here depending on what it is. So for f of 2, the first place you go is to the right, that's the domain, and you just match it to the right category. So 2, which category does it fit into? It's not less than 2, it's not greater than 2, it is 2. So f of 2 is just 4. Okay. For f of -2, it's not going to be this category because it's not greater than 2. It isn't 2. It is less than 2. So we're going to plug it into this one. So we'll do -2 plus 1 squared plus 2. That's going to be 1 here because it's -1 squared is 1, but negative, so this will end up being 1. So f of -2 is 1. Okay. For f of 5, again, same process. It's not less than 2. It isn't 2. It is between 2 and 7. So we'll do 5. So it's just going to be 5 minus 9, which is -4. For f of 10, 10 is not less than 2. It isn't 2. And it's not between 2 and 7. So this is undefined because it doesn't fall into any of these categories. Okay. All right, 7. We are now graphing piecewise functions. This is like the quiz. This is like a quiz question, and this is also from the delta here. So f of x is negative 6 between negative 5 and 1, and then it's x minus 3 from 1 to 5. So remember, when it's negative 6, this is just a horizontal line. This has no slope. So we're going to go over to negative 5. We're going to go down to negative 6 right here. It's going to be a closed hole because it's greater than or equal to here. And we're going to go until 1. So we'll keep going. And then at 1, it's going to be an open circle because it's just the less than sign here. Okay? X minus 3 from 1 to 5. So we're going to pick up back at the 1. We're going to plug a 1 into this. So it's 1 minus 3 is negative 2. That's our y value. So we're going to go 1, negative 2. It's going to be open there as well because this is open. And we're going to keep going until 5. Now my slope here, because it's just x, is 1. So I'm just going to go over 1, up 1 until I get to 5. Well, that's 2, that's 3, that's 4, that's 5. And it's going to be closed at the end. Okay. Another way that you could do this one, if it's a line, is like you could just get 2 points and connect the dots, but make sure you end it at the 5. This is my ending. My domain here would be from negative 5. So we're including negative 5. And we would go until the 1. We don't include the 1. See how it's open there? And then we're going to pick up back at the 1, and we'll go to positive 5. The range would be negative 6. And then it would also be from negative 2 to 2. Open at the negative 2, closed at the 2. Because the negative 2 is open here, the 2 is closed. Okay. This one, you're doing the opposite. So it's giving you the function, and you are writing it out. So we have f of x, curly brackets, and we're going to have our functions here, and then you just go ahead and write the 4's here so you can sort of divide it up. So let's start with the easy one. This is a straight y value. This is just negative 3, so that's easy. It's negative 3 from 0, so when x is greater than 0, but x is less than or equal to 6. Okay? F of x is this function here, which I can see by looking at it. It's got a slope of negative 1, so it's going to be negative x. And the y-intercept is 5, so I see that's negative x plus 5. And that's for when x is less than 5, because it's, sorry, less than 0, my bad, because it's open there at 0, but it's greater than or equal to negative 3. Okay, so domain for that function will be from negative 3 to 0, and then from 0 to 6, and the range would be negative 3 and from 5 to 8. So again, the domain is the y values. The domain is the x values. The range is the y values. The domain, we go from negative 3 to 0. We take a break at 0 because it's an empty hole here, and then we pick up at 0 and we go to 6. For range, we have negative 3 down here, and then we have from 5 to 8. 5 being open, 8 being closed. Number 9. So we have two functions, f of x and g of x, and we're doing different functions on those functions. So for f minus g of x, you just subtract them. This is just saying it's the same as f of x minus g of x. So we're just going to do negative x minus 12 minus x squared plus 7x minus 7. I think the mistake that I'm worried about here is that you may not distribute that negative to all these terms. I want you to take note to distribute this negative to all the terms. Okay, so when we rewrite this, it's going to be negative x minus 12 minus x squared minus 7x plus 7. So when we reorganize this, we're going to get, negative x squared minus 8x and minus 5. And that would be your answer. Okay? So this just means subtract the functions. Just make sure to distribute that negative to all the terms. F plus g Same idea, it's just f of x plus g of x, and that would be negative x plus 12 plus x squared plus 7x plus minus 7. Here you don't have to worry about distributing, you're just going to add everything together. We're going to get x squared plus 6x plus 5. That's it. Okay. For this one, this is like, I put this on purpose. This one here is multiplication, right? That's multiplication. This is not multiplication, this is composite. So you got to make sure you know the difference between the open and the closed. For multiplication, the easiest way to do this, since we've got like a trinomial and a binomial, it's got 3 terms and 2 terms, we can do like a big rectangle, and we can do negative x and a negative 12, and on top we can do x squared, 7x, and a minus 7, and we can multiply these together. We're going to get negative x to the third, negative 12x squared, negative 7x squared, 7 times 12. That's 60, 24, 84, negative 84. Yeah, is that right? Am I? Yeah, that is right. Negative 84 times tables, guys. They'll get you. They'll keep getting you. And then 7 times 12, 84. Okay. Add these all together. We get negative x cubed. We'll combine these two. Negative 19x squared. Sorry, there's an x here. And minus 77x plus 84. Okay. That's it. That's multiplication. Composite, you put one inside the other. So for f of g of x, I would recommend like rewriting it. That's f of g of x. Make sure you like know which one's the big one, which one's the small one. The big one is the f. So go ahead and just write the f out, and we're going to leave that x blank, like put a big like, parentheses there. And then what goes on the inside? The g goes in the inside. So in there, we're just going to put x squared plus 7x minus 7. We're going to distribute that negative through the whole thing. Negative x squared minus 7x plus 7, then minus the 12. We'll just combine the 7 and the negative 12, and we'll get negative x squared minus 7x minus 5. Okay. For the last one, it's division, and I said leave it unsimplified. All this means is put one over the other. It's x squared plus 7x minus 7 over negative x minus 12. You don't need to do anything else. That's a different chapter. We'll work on long division. This is fine. So this is just the same as g of x over f of x. Okay. Nearly there. 2 more pages. 10. Describe the transformation from the parent function and then sketch it. So this one I kept from the previous practice test. If you think about the parent function here is root x. So what happened here? We put a negative out front. So this is going to flip over x axis. That's that negative out front. And this minus 3 inside is going to shift 3 right. Okay. Now, hopefully you're familiar with the fact that what this looks like, it looks like this, roughly. Root x looks like that. So as long as you know what the function looks like, and I'll give you relatively easy parent functions, maybe even easier than this, what I do need you to know, very, very important, is on your toolkit, the vertical shift, the horizontal shift, the flipping across the y-axis, the flipping across the x-axis. You have to know those. So it's, we'll do that at the end of the video maybe. But for this one, we'll shift it 3 to the right, so it means 1, 2, 3 to the right, and then over the x-axis, so it's going to look something like this. It doesn't have to be perfect, guys. That would be fine. Okay. The original, just so you're clear, would look something like this, and we moved it 3 to the right, and then we flipped it over here. Okay. So know how to flip and know how to shift. Know how to do this. Okay. All right. Next one, 11, inverse. So remember, the steps for inverse are you change f of x to y, 2, you switch x and y, and then 3, you solve for y. Okay. So here, let's do the steps. We're going to have y equals 6x plus 5 over 3x minus 1. Let's switch them. We're going to have x equals 6y plus 5 over 3y minus 1. And we'll solve for y. To solve for this for y, you want to get all the y's on one side. We're going to multiply both sides by 3y minus 1. It's going to cancel that. And then I'm going to distribute on the left here. We're going to get 3yx minus x equals 6y plus 5. I want the y's on one side, so let's move that x over, plus x, and then a minus 6y here. So now we have 3yx minus 6y equals x plus 5. Then we'll factor out that y, 3x minus 6 equals x plus 5. And then we'll divide both sides by 3x minus 6 by 3x minus 6, and that's your answer. It's this right here. This equals y. So just to recap, you switch them. So f of x becomes y, you switch x and y, and you solve for y. To do that here, you have to multiply by the denominator, then you distribute. You get anything with a y on one side, you get everything else to the right, and you factor out the y from those terms that both have it, and then you divide by what's left over. Okay, so the last step here says verify. To verify if this is the inverse of this, when I composite them, they should end up the same. So I'll show you how to do that. Some blank paper here. Okay. So right now I have f of x equals 6x plus 5 over 3x minus 1. And I have the inverse is x plus 5 over 3x minus 6. So when I do this, when I do the f of the inverse, I should get x. That's the verification. So let's do that. So everywhere I have an x in my original function, I'm going to replace it with this. So it's going to be 6 So this should equal x, basically, when we simplify this. Okay, so let's rewrite this a little bit. We can rewrite this as 6x plus 30 over 3x minus 6 over 3x. Oh, this is minus 1 right here. 3x plus 15 over 3x minus 6. There is a plus 5 up here, and then there's a minus 1 here. Then we will add, we're going to change this 5 into this fraction, so we're going to rewrite this as 6x plus 30 over 3x minus 6 plus 15x minus 30 over 3x minus 6 over 3x plus 15 over 3x minus 6 minus 3x minus 6 over 3x minus 6. So that 5 I converted to this kind of fraction. This 1 I converted to this kind of fraction. So like this, right, 3x minus 6 over 3x minus 6 is 1. It's just another way of rewriting it, and I rewrote it so that we could combine these two. So here 15 plus 6 is 21. So this is 21x over 3x minus 6. And on bottom we have just 21 over 3x minus 6. Okay, and this is the same as 21x over 3x minus 6 times 3x minus 6 over 21. That cancels, that cancels, that cancels, that cancels. So you just have x. So I don't think I'm going to give you anything quite as challenging as this. The concept that when you take the composition of the function and the inverse and you should get x, you should be familiar with that. But this process here, this is a really tough problem. So I'll avoid anything with really hard algebraic manipulation, but do be familiar with this concept that f of the inverse is x. This is important. Okay. All right. All right, last page. Let f of x equal 3x squared minus 5, and g of x is 2 over x. Find the function f of g. Give the domain of the composition. So f of g, let's rewrite this, f of g of x. My big function is the f, so it's 3 something squared minus 5. What are we squaring? We're squaring 2 over x. So let's simplify this. We can rewrite this as 3 times 4 over x squared minus 5. When we think about the domain, this is the answer, right? When we think about the domain, remember, you're looking for two things. You're looking for zeros in the denominator, or you're looking for the square root of negative numbers. There's no square rooting here, so we don't have to worry about that. There is a potential for a 0 in the denominator. What x value could get you a 0 in the denominator? 0. So x cannot equal 0. So your domain is going to be, we could write x is all real numbers, but x cannot equal 0. Okay? All right, last problem. The graph shows a percentage of students in the Middle East and North Africa who are not enrolled in primary or secondary school. Okay, so you can see that makes sense, right? In the 70s, lots of students are not enrolled. As we get towards the 2020s, they are enrolled. Describe how the percentage of students who are not enrolled in school is changing over time. Yeah, it decreases, right? Decreases from 1970 to 2010, and then flattens in 2010.
Can I ask you a question really quickly?
All right, wrapping up here. NFT represents the percentage of children not enrolled in school. What type of function could be used to explain the model of n? So this is what we did in the last class. If you look at this, it definitely looks like two kind of separate functions. We have like a linear kind of decrease here, and then it flattens out here. That is going to be a piecewise, right? We have, it's because there's two distinct patterns, right? If the data looked like, like this, I would say, oh, that's a quadratic, right, for example. But it varies, sorry. So this is a piecewise function. Do you think the model we chose in part B would be good in predicting the percentage of students not enrolled in school in 2030? So basically what that's asking is this going to continue if we think about 2030 over here? Is it just going to stay flat? I think this is up to your interpretation, and I would accept if you had a good argument, yes or no. I think we would hope, right, that this is going to come down closer to 0, but also it looks like the trend is flat. So I think it would be reasonable because of the trend. But you could also make the argument that it's going to get lower because things will get better and more students will be in school. There's that argument too, but I'm being pessimistic. D, give the domain and range restrictions that should be used for your model of n. So, well, the range, right, the range has to be from, it can't be any lower than 0%, and it can't go higher than 100, so that would be the range. This is percentages. And then the domain, well, we start our model in 1970, so, maybe we could go back in time a little bit, but let's not. So let's say the domain maybe is from, let's say 1970, that equals 0. So our domain is going to be from 0 to I mean, I guess going to 2030 is reasonable. So we could go from 0 to, I would accept 0 to 40. I would also accept like something like 0 to 50. Basically, that's like how many years can we go? We could go like, you know, you're not going to go thousands of years in the future, right? That doesn't make any sense. But something reasonable, like going 40 or 50 years, seems like reasonable for our model. Much more than that doesn't seem that reasonable. And we're done in a half hour.